Okay, so we've just finished our lecture on the spectral theorem. Remember, the spectral theorem comes in three parts. The first part, in the point of the spectral theorem is to better understand Hermitian matrices. The first part says that every Hermitian matrix has eigenvalues that are all real numbers. The second part says that the eigenspaces of a Hermitian matrix are orthogonal to one another. And the third part says that every Hermitian matrix is guaranteed to be diagonalizable. Now, that's sort of the ugly way to state it. And remember, we proved two of the three parts, so that's pretty good. But the elegant way to state the spectral theorem is to say that every Hermitian matrix is defined by the property of having a spectral factorization. A spectral factorization is a diagonalization of the matrix by a unitary matrix. In other words, every Hermitian matrix H can be expressed as a unitary matrix U times a real diagonal matrix D times the inverse of U, which is the conjugate transpose of U. Now, I've written some code here in Sage that will take a Hermitian matrix H as its input, and as long as the eigenvalues of this matrix are nice enough, this should give us a spectral factorization. So remember, the method for finding a spectral factorization says find the eigenvalues, and then find bases for the eigenspaces, and apply Gram-Schmidt to each of those bases. Once you apply Gram-Schmidt, when you diagonalize using those vectors, the matrix that you're filling up with eigenvectors is guaranteed to be unitary. So let's click Evaluate on the code that I've predefined here and see what happens. Cool. So I've input a Hermitian matrix H here. And what this code is doing is it's giving me U and D, or at least a valid choice for U and a valid choice for D that will give me a spectral factorization. So I input this 3x3 Hermitian matrix, and so this is giving me a valid choice for U and a valid choice for D here. So feel free to use this as you're working through problems, but also you want to make sure that you understand what is going on in the background here. We're finding bases for all of the eigenspaces, and then we're applying Gram-Schmidt to each of those bases. So you can see here in the code that I've written, I'm kind of constrained by the HTML requirements of my website. So it's hard to write this out like line by line. So what I end up doing is I end up writing stuff all in one line, which is not great practice. But you shouldn't be surprised here that Gram-Schmidt is popping up in the code I've written. That's because I'm applying Gram-Schmidt to all of the bases of all of my eigenspaces here.